Welcome, my friends. In this video, I'm going to discuss two-way tables. If we would like to consider two variables related to a single individual together, then we have what is called bivariate data. If both of those variables are categorical, meaning they are not numerical or quantitative, then this data can be summarized by what is called a two-way table, sometimes called a contingency table, and that would look something like this. So in this case, we have two categorical variables. The first variable is education type, which has two different levels. We have either no college degree or college degree. Our second categorical variable is employment status, which we have either employed, unemployed, or not in the labor force. This is a categorical variable, or both of these variables are categorical variables, because they are not numerical. We are placing people into these different categories or groups, right? Either no college degree or college degree. Those are categories, just as are the employment status categories, where either employed, unemployed, or not in the labor force. Now we do have numbers in here, and that's just because we're counting how many individuals fall into each of those categories. So for example, we have 130 individuals who are both not having a college degree and are employed. Or we have 7 people who do have a college degree and are not in the labor force. That would be individuals not even looking for work. Unemployed typically means you do not have a job and you are actively seeking a job. We also have row totals, which represent the total of each of the row variables or levels of the row variable. So there are 200 individuals who do not have a college degree, for example. Or we also have the column totals, which refer to how many individuals we had in total for each employment status. So for example, there were 71 people who are unemployed. And then we also have the grand total of 550 individuals who were surveyed for this table. And you can also always find the totals by adding up. So you can notice here 130 plus 50 plus 20 does equal 200, or 20 plus 7 is 27. So everything does all add up. Also along the column totals, if we added these three numbers up, we would get the 550, as well as if we added these two numbers together. So specifically in this class, this is not always the convention used, but in this class, we're going to view the row variable, which in this case is our education level, as being our explanatory variable or independent variable. And we're going to let our column variable, which is employment status here, represent our response variable. So that means that we may have the belief that our education level or someone's education level might have some influence on their employment status, right? And not necessarily the other way around. We may have the belief that depending on your education level, you are more likely to be, for example, employed, unemployed, or not in the labor force. Okay, so we're typically going to view our row variable as perhaps influencing our column variable. Now, another term here that we might use sometimes is observed cell count. And by that, we just mean every single value inside of the table is just something that we've observed from our survey. We've observed that 21 people had a college degree and were unemployed. That would be considered an observed cell count. There's something later that we will talk about in the context of what is called a chi-square test of independence, called an expected cell count, but we will worry about that later. For here, we're just worrying about the observed cell count. So here's another example of that. We observed 130 individuals who were employed and also had, and I think this should say does not have a college degree, but it says with college degrees, but that should have said with no college degree. All right, so instead of expressing a two-way table using those observed counts, we can express each cell as a proportion of the total sample size. And this creates what is called the joint distribution of our two categorical variables. So basically, instead of expressing everything as a number, we're going to express everything, I mean, there'll still be a number, but it's going to be a percentage out of the total, or a proportion out of the total. And to do that, all you have to do is take every single value in your original table and divide by your total sample size. And that would end up looking something like this if we put those in percentage forms. So the way that you would get this table down here is you would just take each value and divide by your total sample size. Let me just show you a few of those with this basic calculator here. If I took 130 and I divided that by 550, my grand total, I would get 0.2364 rounded to 4 decimal places. If I multiply that by 100, I will get that in percent form, 23.64% rounded to 2 decimals there. It's exactly what we're seeing right here. Or any of the numbers, right? I could take this 200. I could take the 200 and divide that by the grand total of 550. And that would also give me the correct value, 0.3636. And I think that the way I got this, this is off by 1 decimal place, is because you can also find the totals by adding up the rows. And I think that must be what I've done here. If you add up these 3 together, you would get the row total. And sometimes due to the rounding, we can get something slightly off. Okay, so this is what we call the joint distribution. And now each value is just thought of as a percentage of the total. So for example, 58.55% of the people were employed. And once again, yeah, and I do have it right this time, employed with a college degree, 58.55%. So over half the people were both employed and had a college degree. Or about 63.64% of people in total had a college degree. So a little bit maybe easier way to digest the numbers in terms of how big they are relative to the whole total sample size, and that is what we call the joint distribution. Now there's one other distribution that you might want to create based on this information, and that is what we call the conditional distribution. And this is going to tell us how likely an individual is to be part of each column of the table, given or assuming that they are part of some specified row. I know that's a little wordy here, so let's look at what we mean by that. The way that you find the conditional distribution, in this case of the row variable given the column variable, would be you would take each row value and divide by that row total. So we would take, for example, the 130 and we would divide by the 200 and we would get 65%. Let me show you that really quick here. If I grab my calculator again, if I took, let's take the 130 here, 130. And now instead of dividing by the grand total, if I just divide by the row total, which is 200, and I think these numbers come out a little nicer, I get exactly 0.65, or if I multiply by 100, I will get the percent form, which is 65%, right? Or if I took the 21 here, maybe I'll take the 21 and divide by the row total of 350. And let's try that one more time. 21 divided by 350. And then I would get 0.06, which is the 6% that I have right here, okay? And what these values are telling you, it's telling you each value as a percent of the row total, because we're dividing by the row total. That should make sense, right? So for example, 25% of those without a college degree are unemployed. So it's saying just focus on one row at a time, just out of the people who do not have a college degree. What percent are employed? This is not out of the total. This is out of just those who do not have a college degree. So of those who do not have a college degree, 65% are employed. Or of those who do have a college degree, 92% are employed. So these are given or conditioned upon, why we use a conditional distribution. They're conditioned on each of these row values. Okay. You could also do a similar thing based on the columns, but since we're using the rows as our explanatory variable, it's a little bit more common to just think about it this way, only by dividing by the row totals. So that is the way that we're doing it here. Now, the main reason why you would maybe create a conditional distribution is to assess what is called independence. So we may want to assess the independence of the variables. And let me try to explain what I mean by that in the context of this example. So education level, our row variable, and our column variable of employment status would be independent if individuals are just as likely to be employed regardless of their education status. So that would be like saying, it doesn't matter if you do or do not have a college degree, you're just as likely to be either employed or unemployed or not in the labor force. It doesn't make any difference which category you're in over here, right? Alternatively, the variables could be dependent. And that would mean that individuals in one of the categories of the row variable are more likely to be in certain categories of the column variable, or specific to our example, particular individuals are more likely to be employed based on their education level. So that would mean like, maybe it's more common for people who have college degrees to be employed. If that kind of played out in the data, then we would say that our variables are dependent. So think about this for yourself for just a moment. See if you can determine if education level and college degree are independent based on the data here. And think about how you would make that determination. Well, the way you look at that, you make that determination is you just compare for each column the percentages. So for example, you would compare the 65% and the 92%. This 65% says, of those who do not have a college degree, 65% are employed. Of those who do have a college degree, 92% are employed. So that's telling me that these are probably dependent, right? These two variables, these two variables are dependent, because if you do have a college degree, you're a lot more likely to be employed. Or if you have a college degree, you're a lot less likely to be unemployed, right? 6% compared to 25%. So basically, you're just matching up the numbers. And if these numbers are much different from each other, looking like top to bottom, in each of these different categories, then that's going to suggest dependence of the variables. So are the variables independent? No. Individuals with a college degree are much more likely to be employed. Employment status depends on or is influenced by education level. Now, I should make the caveat that this dependence does not necessarily suggest a causal relationship. Probably does to some degree in this example, but by causal, I just mean that in isolation, changing the row variable should change the column variable. We haven't proved that in this type of example, so we just know there's some kind of relationship there. Is it causal? Maybe, maybe not. We will talk more about causal relationships in a future video. An even easier way to assess the independence once you have the conditional distribution is to simply graph each of these categories. So that would look something like this, right? So I have employed, I have unemployed, and I have not in the labor force, and I've graphed the conditional distribution for each one. And now it's even easier to see that there's kind of a big difference here. There's a lot of the people who have a college degree, 92% are employed, only 65% of those without a college degree are employed. Note that these are not real numbers, so don't take them too seriously. This is probably more of an extreme of a difference than you might see in the real world. Okay. So if you wanted to assess independence based on bar charts, you would graph the conditional distribution, each column together, and then you would assess whether or not the bar heights are close to each other or far apart from each other. So if you have similar bar heights, that suggests independence, and if you have much different bar heights, that's going to suggest dependence, as we have in this particular example. All right, my friends, that completes this video discussing two-way tables.